So what you'll find is that on the sheet, it talks about this position and they give you various quantities, and this one various quantities. And then from those, we can kind of figure things out as we go. Okay. So let's go in. Let me find a couple of examples for us to work. Okay. So let's take a look in chapter 11. At number 35. Yeah, so I think that this one doesn't seem as complete. As the information that we learned before. And part of this is because we're going to kind of quit doing things from the ground up and understand every single little bit and piece. And we're going to move away from what I tend to call first principles type of problems, and then move more to like second principles, where it's like, here's the governing equation, this is how we use it, and then we'll do some examples, instead of let me figure everything out from the ground up kind of things. So it's going to change a little bit. So 35 reads that one end of a stretched ideal spring is attached to an air track and the other end is attached to a glider with a mass of 0.355 kilograms. Okay, so we have a little air track. Air track. Have a little glider. Attached to the spring. There's my little air track. And my glider. Okay. And so it says, oh, the mass is 0.355. That's the mass of the glider. And so, like I said, if we can figure out K, the spring constant of our spring, M, the mass of the object attached to the spring that is undergoing the simple harmonic motion, and then A, the amplitude of that particular motion, then we can pretty much answer nearly any question that they want to ask us about. Okay. Because everything for the simple harmonic motion is written in terms of those particular quantities. Okay. It says the glider is released and allowed to oscillate in simple harmonic motion. If the distance of the glider from the fixed end of the spring varies between 1.80 meters and 1.06 meters, and the period of oscillation is 2.15 seconds, find the force constant of the spring, so find K, and find the maximum speed of the glider, the Vmax, and then the magnitude of the maximum acceleration of the glider, Amax. All right. So we have that it's going to go simple harmonic motion, and it's going to oscillate back and forth such that the distance varies between, this end here and this point versus that point. And they say that this piece was 1.80, 1.06. This will be the 1.06 meters. And then it says that the period of the oscillation is 2.15 seconds. Okay. So when we look at this oscillatory motion, you know, down and back, down and back, down and back kind of things, then notice that if we go in and look, they're describing from here to here, okay? And so what you have is that this is an amplitude's worth of distance from the equilibrium to this point. And then from the equilibrium to that point, it's another amplitude worth of distance. So really what you get is that this full distance that they have here, this is technically 2 times the amplitude. You know, so there's the equilibrium in the middle. We would have A here and A there. So the full run is 2A. Okay. And so we can use this information, the 1.8, the 1.80, and the 1.06 to then solve for this 2A. So let's do that. So 2A will be 1.80 minus 1.06 meters. If we divide both sides by 2, then we can get the amplitude of the oscillation. Turns out to be how much? Point 74 cut in half. Yeah, 0.37. So we've got the amplitude, we've got the mass. All we need is K. Now, if we look, they gave us the period. So this is tough. I mean, given this from 1.80 to 1.06 is the motion, coming out that that's 2A isn't super obvious. But then if we look at the period is 2 pi square root of m over k, and we know m and we know the period, then the only unknown is k. Okay, so let's take a look at that. So the period is equal to our 2 pi, as I write the wrong things down. M over k. As we know, this is 2.15. It's 2 pi square root of 0.355. We can solve for k. So to solve for k, we're going to divide both sides by 2 pi. This. And so what do we get for our 2.15 divided by 2 pi? Dividing by 6 or so. So I think it's another 0.3-ish kind of number. Yeah, we got to watch the parentheses on the 2 pi. It's super easy mistake. But 2 pi is kind of like 6 or so. And 2.15 divided by 6 is going to be like 0.3-ish, kind of, sort of. 0.34. Thank you. Now, to get the k out of the square root, we're going to go in and square both sides. And then that'll give me this value. So then I can move the k over to here. And I can move this 0.34 squared down to the denominator there. Okay. And so this will give me that k, the spring constant, is 0.355 divided by 0.34 quantity squared. And so what do we get for k? 3.07. This should be newtons per meter for our spring constant. Okay, there we go. And so then, question A. And then in B, they wanted the magnitude of V max. So they wanted the maximum speed. And so at this stage, we should have it because we have M, we have K, and we have the amplitude. So, I mean, we should be in great shape. So then our V max is this root K over M times the amplitude. And our K is this 3.07. The mass is 0.355. And the amplitude is 0.37 meters. .09 is all right. And then they wanted the magnitude of A max. And so the A max magnitude is the K over M times the amplitude. So our K is that 3.07. The mass is the 0.355. And then the amplitude is this 0.37. So this should give us that magnitude of the maximum acceleration. 3.2. Yep. All righty. So I think the tough part is going from this 1.80 to 1.06 to get the amplitude. Once you have that, we have the M, we have the amplitude, and then notice that instead of straight up telling us the spring constant or the force constant, they told us the period of the oscillation, and from there we could solve for that K. And so and then again, once we have the K, the M, and the amplitude, you know, we're golden. We can answer anything on the sheet because we know all those values. Okay.